Okay, so a couple quick administrative bookkeeping things. The lectures for Monday and today will be posted onto Carmen tomorrow, along with the questions to ponder for stress. We're going to get back on the Wednesday schedule for quizzes. So Monday there won't be a quiz, but there will be a quiz on Wednesday, right? I will add attendance. Oh well, a beautiful brand new piece of chalk is now unusable. Attendance for onto Carmen. So keep track of it, and if I miss you, let me know sooner rather than later, because it doesn't help. Like at the end of the term, it was like, yeah, I was there on January 24th. But if you tell me like the day after, they're like, oh yeah, you were there. So, okay, so we were going through the equilibrium condition. So I'm just going to write it over here so it's fresh. So we had sigma. All right, and this is the divergence of the stress plus the body forces have to be equal to 0. And so we got that from the sum of the forces, right? So it's a balance of linear momentum. And now we're going to basically do a balance of angular momentum. So just a quick point. We're always going to be worried about the static case. But if we're doing dynamic, right, and we have to worry about inertial effects, does it change anything here? The only difference is instead of being equal to 0, as we said MA at the beginning, right? Except for the fact that when it's dynamic, we still have the differential momentum to consideration. So we have basically our dp dt term over here, right? So that's the only difference between static and dynamic. And we're not going to worry about dynamic for the rest of the class, but everything that we're saying about equilibrium and balance of linear momentum still holds if you just put the momentum term. Okay, so sum over the moments. This is a little more, all right? So we can define a position vector. Right? So that R is our position in the body. So what's our moment? Right? So remember, a moment vector is the cross product of a force and the distance, right? So in terms of indicial notation, right, we use our permutation symbol, right? So we have that. So that's our expression. So we want to set up our balance. So again, we have an integral over the surface. Right, where this is our traction vector. And then we have a volume integral. Right? So the same that we had before. We're going to make a substitution here. Right? I'm going to substitute back in. Oh, let me write it in indicial notation first. So it'll be a little clearer what I'm doing. Right, this becomes the surface. Right. Okay, so now we can substitute in sigma n for our traction vector here. Right. So this becomes sigma m k n m. Right. And then we all right, what did we do last time here? All right, we want volume integrals, right? So we're going to apply our divergence theorem again.
What's the subscript on the sigma?
Oh, sigma mk n m.
Oh, and oh, okay.
Right.
Wait, the n is big though. It's not
This is n, yeah. So this is the normal vector m. Right. So we're going to apply the divergence theorem. If I write here, can everyone over there see? If I write it nice and big. All right. So now we got volume. Okay. Right. So this is our moment vector. Right. The derivative with the normal. So let's this is a derivative here, so let's apply the product rule and expand this derivative out. Right? So that gives us epsilon. Make sure I don't make a mistake with indices here. I, j, k, x, j, comma, m, sigma, m, k. Right? So this is just the product rule, right? First times the derivative of the second, second times the derivative of the first, right? And then we're going to do a little algebra, right? And put everything that has xj into, they're both integrals over the same volume, right? So we can move this, because it's the linearity of it, we can move this from here over to this side, right? So let me write that up here. So this becomes the volume. Okay, so just a little algebra. Notice this here, this is equilibrium, right? So this, by definition, this term is zero. If this term goes to zero, this whole integral has to be zero, right? because the integrand is 0 everywhere. So this term disappears. What about this term? What is this? All right, this is partial xj partial xm. All right, so if that is our position vectors, the basis is orthogonal, right? So what's the derivative of the x-axis with respect to the y-axis? Right, they're orthogonal vectors, so that's 0. Except if j equals m, right? Then it's the derivative of x with respect to x. Right? So this becomes, right, because of the orthogonality of our basis. So then this simply becomes delta j sigma mk, right? And by the properties of the Kronecker delta, right, I can replace this like that.
Can you write that out?
Oh, okay. J, sigma j k dv. All right? And we're going to use the same argument as we did with equilibrium, right? That this has to hold on any subregion of our body, right? And so the only way that that can be true is if the integrand is equal to 0 everywhere, not just the integral, right? So then we just simply end up with I j k sigma j k equals 0, right? And so now here's the magic, right? So we can write this out, expand this out. Epsilon 1 jk sigma jk plus epsilon 2 jk sigma jk plus epsilon 3 jk sigma jk equals 0, right? And so here, for any combination, well, so if the diagonal components of stress, 1, 1, 2, 2, and 3, 3, all of these terms are 0, right? Because then if we have 1, 1 here, we have epsilon, we have a repeated, and always will have a repeated index in the epsilon. So the diagonal components of stress don't contribute to this. All the off-diagonal component terms, let's pick 1, 2. What's the, right? So anything with a 1 or a 2 in it is going to go away. So for 1, 2, the only term that survives is this. And we have 3, 1, 2, sigma 1, 2, plus 3, 2, 1, sigma 2, 1, which gives us that sigma 1, 2 minus sigma 2, 1 equals 0, or sigma 1, 2 equals sigma 2, 1. Right? And the other 6 off-diagonal components, we end up with those same, right, equations. So we end up with the general sigma ij equals sigma ji, or that the stress tensor, the Cauchy stress tensor has to be symmetric. Damn it.
You epsilon I j k times sigma j k equals 0, and right below it, why are you summing your eyes when there's only one piece?
Oh, dang, you're totally right. Never underestimate my ability to make stupid mistakes, right? So this is 3 equations. The result's still the same. Right? That's like a classic exam mistake, right? You make a silly bonehead mistake that gets you to the same result. And the thing is, I have it right here. When I wrote it out, it's correct. Just when I wrote it on the board, right? So this one, there's not so much deep physical insight in the momentum balance. It's just sort of a good exercise in calculus of second-rank tensors. Right. Okay. So in the notes, I then sort of ask you to use this. So we have one point I want to make. So before we wrote traction as this, right? Or traction like that. Normally, if you look in a mechanics book, you'll see, right? See it like this. So in terms of, if the normal is a column vector, that would be a row vector times, right? Because of the symmetry of this, you can write it like this and write it as a typical matrix vector product, right? It's just sort of a nice little fluke with the algebra. There are other stress tensors that are not symmetric, where you have to pay attention to left and right multiplication by your normal. All right, we can define in the notes. I don't discuss them. I just sort of define them and say, here this is sort of like the 3-dimensional equivalent of the true stress, right? We're taking an area in our deformed body and our force in the deformed body. Well, for different situations, you might want areas in your undeformed body with forces in your deformed, or forces in your undeformed frame and areas in your deformed, and that gives you all sorts of different definitions of stress. Right. The most common when we're dealing with finite deformation plasticity is a Kirchhoff stress tensor, which is a not symmetric stress. Okay, but so in the example, I say we have a stress tensor of the form I have a stress tensor that looks like that, and I give the plane 1/7 to E hat 1 minus 2 E hat 2 plus 6 E hat 3, right? And I say, what's the traction, right? So it's just a thing. One, I did make a mistake. So everyone make a quick correction. This isn't actually a unit vector, right? So 36 plus 4 isn't equal to 49, right? So I screwed up in the notes, so this isn't a unit vector. So make this not be n, this is just some plane. We'll call that p, right? And then if you want to make it a unit vector, you get right. So that's your the unit vector that corresponds to this. So this is the normal, right? And so then the traction vector, right, is just sigma n, right? Standard matrix vector product, and I get 63. This was MPA was the units there. Right, and so the units of traction are going to be in newtons, right? So finding the traction on that plane, and then of course the one that is of more practical use is geometrically. So if we have this axis, I have 1, 1, 2. So this is point 1, 0, 0. This is point 0, 1, 0. This is point 0, 0, 2. Right? And so then I've got a normal vector there. How do I find n? Right? I have to go back to all your old geometry. So since we're all materials people, right, we'll use our Miller indices and cubic coordinates, right? And remind ourselves that the direction, right, the Miller indices for a crystallographic direction and the crystallographic plane normal are the same when you have the cubic crystallographic bases, right? So all these fun little things fall out when the metric is the identity, right? Okay, so how do we find the Miller indices of a plane? This were a crystal, right? And our intercepts were 1, 1, 2, right? Well, it's 1 over, right? All right, and then we need to make them all integers, so we multiply through by 2. So this, and then we need to make it a unit vector, right? 2 squared, 4. I wrote it down. Oh, yeah. 4, 4. Yeah, it is 9. Okay. Right. So our unit, our n, is 2/3, 2/3, 1/3. Right. So that's our. That's the normal, and then of course sigma n gives us minus 14, and 77. Right. So just manipulation with stress, finding the forces acting on different planes. Right. Okay.
For enemy, always going to be commenters.
I mean, yeah, that's just the standard way of writing it, right? It's just convenient to write the tensorial operation as a matrix vector product, right? That makes, you can put it into your calculator or MATLAB pretty easily. Right. Oh, we're back. I didn't want to turn that back on yet. So coordinate transformations, right? These were the examples that we skipped from the first, right? And so we have to go back and refresh ourselves, but it's a second order tensor, so stress transforms by A or Q sigma A transpose, right? But we need to do a couple examples of work out how do we find the transformation matrix from for a particular transformation. So in the questions to ponder, all right, so the first one, if we have a 2D coordinate, all right, this was x1, x2, and I said a 90-degree rotation about x3, right? So if this is x1, x2, x3 is coming out of the board at us. And I said a 90-degree rotation about x3 in the sense of a positive right-hand screw, right? So that means, right, so we're rotating. If I put my thumb along the x3 axis and I turn it with my right hand, right, right hand rule, that means I'm rotating 90 degrees this way. Since on the example sheet, I wrote it opposite, I'm going to have to do these live. So everyone check my, right? When I wrote it out, I did it in the sense of a left-handed screw because I wrote my coordinate system wrong when I made my sketch. And I just realized that looking at it now. Okay, so we've got our primes here. All right, and we want to make our dot product, right? So what do we have here? We have x1 going to x2, right? x1 goes to x2, x2 goes to minus x1, and x3 stays at x3. All right? So this becomes x1 prime. This is x2 prime, and x3 prime equals x3. All right? So the dot product between x1 and x1 prime, or x1 prime and x1 is 0. The dot product between x1 prime and x2 is 1. Right? We're still orthogonal here. x2 prime is here, and x1 is minus 1. 0, 0, and 0, 0, 1. All right? So our Q matrix for this case that's our coordinate transformation matrix for the case of 90 degrees. Right? The second one, I ask for a 60-degree rotation. Right? So in that case, our geometry is a little different. Right? So now we have 60 degrees here. Right, this is now x1 prime. x2 prime is here. All right. This is 60. This is 30. All right. So let's take a look at this by we can write the coordinates of the prime with respect to the original, or we can write the coordinates of the original with respect to the primes and fill in our chart. It doesn't make a difference, right? They're both equivalent because it's always only about the angles between them. So let's write the coordinates of the new with respect to the old, right? So this vector here, right? This becomes a 60, 30, right? So 1 and 1 prime, right, is the cosine of 60, right? What's the cosine of 60 degrees? What's that? Square root of 3 over 2, right? E1 prime and E2 is 30 degrees, right? So the cosine of 30 degrees is going to be 1/2. Right? Cosine of I even did this. I'm giving it. No wonder why my notes don't make sense. Because we did it around x1 in the notes. But anyway, we'll do it about x3. It works out the same. So I should have here x1 prime. Now that I'm on the spot, does someone who knows their trig tables really well? 45 is square root of 2 over 2. Yeah. Right? So cosine 60 is 1/2. Right? So this is 1/2. This is square root of 3 by 2. Right? Then this is E1, E2 prime. That's cosine of 150. Right? So that's minus, what's that?
X1 prime and X2 prime?
X2 prime and X1. Oh. Right? So 60 and 90 is 150. So what's the cosine of 150? Minus square root of 3 over 2. Right? And now X2 and X2 prime, that's 30 degrees. Wait. What's that? This can't be right.
It's negative, right? It's negative x1.
So this is x2 to x1, right? So this is the cosine of 150, right? Is that minus square root of 3 over 2?
Yeah, that's pretty negative.
It has to be negative, but is it negative 1/2 or minus square root of 3 over 2? Well, this has to be a unit vector, right?
It's 30 degrees. It's 30 degrees from 180.
Yeah.
So it's
okay.
negative of 30.
Yeah.
Which cosine of 30 is square root of 3.
And x2 prime x2 is 60, so that's 1/2. Yeah, that's right. Okay. So this is our Q. Right? So that's the procedure. Right? Most of the time when we do these in practice, we're doing it about crystallographic axes, right? So a common one with respect to deformation in FCC is 60 degrees about 111, right? Why is that going to be common, right? What's the slip systems in FCC, right? They're the 111 planes in the 110 direction. So we have a triangle of slip directions on the 111 plane in FCC, right? So crystallographic, right? Those are crystallographically equivalent directions. So 60 degrees about 111, right? 45 degrees on the 110, right? These are types of things that we're gonna coordinate transformations that we're going to see quite common. Okay, we are okay. So back to actual notes. Oh, 1 point. So if I want to compose coordinate transformations, right? How do I do that? If I did a rotation by 90, if I did a coordinate transformation that is equivalent to a rotation by 90, and then I did another coordinate transformation of rotating my coordinate axes by 60, right? How do I do it, right? So Q is equal to Q1, Q2. It's left multiplication, right? I do this action first, followed by this action, right? So we can do composition in that way. Okay, so an really important concept with respect to stresses is the notion of principal stresses and principal stress directions, right? And what this means, right? So as we showed before, for a general point, the traction vector is not necessarily collinear with our normal vector, right? Our force acting on the plane is not always normal to the plane. We have components, shear components in the plane, right? But there is going to be, at any point, there is guaranteed to be 3 planes that I can cut on that are going to be orthogonal to each other, where the traction vectors are orthogonal to those planes, right? So those of you schooled in linear algebra, how can I confidently make that claim? Not necessarily cross product, right? So yeah, eigenvectors, right, and eigenvalues, right? How many is stress we just showed as a symmetric matrix, right? Symmetric tensor, right? How many real eigenvalues does a symmetric matrix of real components guaranteed to have, right? Right. Any square matrix is guaranteed to have 3 eigenvalues, but they might be complex, right? Might have complex eigenvectors. But because it's symmetric and it's real, we're guaranteed to have 3 unique eigenvalues. Or not necessarily unique, 3 real eigenvalues. They might be repeated, right? And then we're going to have 3 orthogonal eigenvectors, right? If you don't necessarily follow that logic right now, we'll work through an example, right? And it should be a little bit clearer, right? So what we're saying physically is if the traction vector and the normal vector are collinear, or the traction vector is orthogonal to the cutting plane, that means that the action of the stress tensor is just scaling our normal vector, right? So that means the planes where this occurs has a unique form. So we basically say sigma ij nj is equal to, instead of using sigma again, I'll just write it like this, right? Meaning that the action of the tensor on n is to simply scale the normal vector, right? So remember, I talked a little bit about linear transformations at the beginning of the first lecture, right? And I showed the eigenvalue example, eigenvector example. It said for a linear, arbitrary linear transformation, I can go from a sphere to an ellipse, right? And the eigenvectors are the vectors that don't change angle in this transformation. The eigenvalues are the value by how much our eigenvector is stretched, right? Right. So I think I've got just enough time to work through this. Right. So for those of you who need a little refresher, remember we're solving sigma n equals lambda n. This is the equation that we're interested in. Or sigma ij nj equals lambda ni. Right? We bring this over, sigma ij nj minus lambda ni equals 0. And then I can pull the n out, sigma ij minus lambda delta ij j equals 0, or sigma minus lambda I n equals 0. All right?
So no matter that your indices are different.
Well, that's why I had to use this delta here, right? Because this is, right, this here is a scalar, right? So what I need to do is make sure that I'm subtracting the right terms from the right terms, right? So that's where that delta comes from. Okay. So I've got this system of linear equations here that holds true if this is true, right? What do I know if this has a solution? What do I know about this system of equations? Right? Well, probably learned this even before linear algebra. Algebra 2, I would think. And I guarantee almost everyone's forgotten it. There's a statement that says this has a solution if and only if the determinant of the system is 0, right? So this determinant has to be 0, right? So our system of equations, right, if we expand it out, right, sigma 1, 2, right? Or, right, the determinant here is just right. So this is how we find our eigenvalues. It makes more sense if we throw in some numbers and do a concrete example. Right. So if we have a stress, 57, 0, 24, 0, 50, 0, 24, 0, 43. Why did I pick one with this strange form? Right? This way I end up not having to factor. Right? For those of you who've done eigenvalue calculations by hand, I have something easier to factor. I know right away one of my eigenvalues is 50, but we won't jump to that. So the determinant that we're looking for, that we want to solve, right? Okay. How do we find the determinant of a 3 by 3 matrix? Remember, how do we find the determinant of a 2 by 2 matrix? Right? That's this minus this. Right? So that's the determinant of a 2 by 2. For 3 by 3, we have to do our cofactor expansion, right? So we do this. We write down our first cofactor, right? Times, we block out this row, and this column, and now we have a times this 2 by 2 determinant. Right? And then it alternates, right? Plus, minus. I can either go down the row or across. I'll go across down the column or across the row. I'll go across. So then minus 0 times some other determinant, right? So I'll write it out. If I do this and this, it would be 0, 0, 0, 0, 24, 43 minus lambda plus 24 times 0, 50 minus lambda, 24 is 0. Right, now I can do all these, this whole thing has to equal 0. I can do these determinants here. All right, this is 0, so I get 57 minus lambda, 50 minus lambda, 43 minus lambda, plus 24 minus 50 minus lambda times 24 equals 0. And if I do my algebra and factor it, I end up with 50 minus lambda, lambda minus 25, lambda minus 75 equals 0. Right? So that gives me my 3 eigenvalues as 75, 50. So what does that mean? Right? It means that somewhere there is some coordinate transformation that I can apply to this tensor, and I'll get out this diagonal tensor, right? So what I have is sigma p is q sigma q transpose, right? But I don't know what that coordinate transformation is yet. I still need to find that, right? So how do I do that? Now, I plug it back into my original system, the eigenvalues back into my original system of equations. Right? So for lambda equals 75, right, I plug it back into my sigma minus lambda I n equals 0, right? So I do 50 minus 75, 0, 24, 0, 57, 50 minus 75, 0, 24, 0, 43 minus 75 times n equals minus 18, 0, 24, 0 minus 25, 0, 24, 0 minus 32 times n equals 0, and the solutions to this system of equations are, right, I end up with the equations 4 and 3 equals 3 and 1, n2 equals 0, and I know that n has to be a unit vector, so n1 squared plus n2 squared plus n3 squared equals 0. I mean 1, dummy, right? And so that gives me n equals plus minus 4/5, 0 plus minus 3/5. Right? And we can do the same thing for the other two systems. For lambda 2 equals 50, anyone know what the eigenvector is going to be off the top of your head? N2 has to be 0, 1, 0. And then for lambda 3 equals 25, the vector is plus minus 3/5, 0 minus plus 4/5. Right? So that tells us that those are our eigenvectors. These are orthogonal unit vectors. Right? So that's our coordinate transformation matrix. So Q, to go from the regular frame into the principal frame, is 4/5, 0, 3/5, 0, 3/5, 1, 0, 0, minus 4/5. And you can try that out by yourself and see principal. The principal stress is Q sigma Q transpose. Right, so that's how we put the stresses into the principal frame. So the eigenvalues are the principal stresses. The eigenvectors are the principal stress directions. Right, they tell us those are the three directions in our sample that our traction vectors are all just three orthogonal vectors that are aligned with our x, y, and z axes. Right? So no, I do not want to update. Thank you, Word. right? So that's sort of, oh, and that's, we're out of time. So we have like one more slide left on stress. And on Monday, we'll do strain, which is a little bit less mathematical. Well, a little bit less board writing, right? A little more straightforward, I think.